There's an American folk saying that goes like this: there are only two certainties in life, death and taxes. And while maybe this speaks to how Americans view tax agencies, it also speaks to the fact that uncertainty is present all over in our world. And in our code, because we try to model the world and the processes that happen there, that uncertainty also manifests itself in a lot of ways. As programmers, we like to have a nice linear path, operation, another operation, another operation. And uncertainty forces us to add a lot of conditionals to handle all of these special cases. Things like errors and data that's absent. So uncertainty can come from a variety of sources. User input is a very common one. You never trust what the user sends you. It can also come from other systems. If you're connecting with some API, you can't really trust that their input is going to be correct. Finally, it can even come from within your program. Depending on the way you have your data structures and the operations that you do on them, you can generate uncertainty from within. Today, we're going to take a look at sort of my journey, learning to deal with uncertainty in Elm, and eventually finding enlightenment with union types and everything in between. So you're a software developer, and you've just been hired for this fancy society for the preservation of vowel names. Their mission is in the name. They like names that start with vowels, and they want to preserve them as an artifact of society. And so, as a nonprofit, they receive donations from all sorts of people, and they've hired you to build software to display a list of those donors. Here are the requirements. They want all names to be lowercase, but donors whose names start with a vowel, who sort of doubly support the mission, we're going to put an asterisk in front of their name to mark them as special. And then finally, some people prefer to donate anonymously, and so we're just going to write anonymous. Note that anonymous starts with the letter A, that's a vowel. Do not put an asterisk in front of that. That doesn't count. So if we were to represent this as a diagram, we might sort of show this, this flowchart like this. So we have a user who may or may not have information, and then if they're not present, we display anonymous. Otherwise, we get their name, we lowercase it, check if they start with a vowel, and optionally prefix it. And this is kind of the interesting part down below, the sort of the core business logic. So if we ignore the anonymous users for a second and take a look at how we might write this in JavaScript. So we have a function here, and we take in a user as an argument. And if the user's name starts with a vowel, we prefix it with a asterisk and lowercase it. Otherwise, we just lowercase it, and we're good. Now the question is this safe? Well, the answer, I don't know, maybe, maybe not. It really depends on how that function is used. For example, if we have a user who's just set to null and we pass that into display name, things will blow up. If we have a user that is present but the name is null and we pass that into display name, it will blow up. The problem is that you can never trust anything. Arguments, variables, return values. The only way to make sure is to manually check everything. And that is just way too many conditionals. That's too much work for us to do as programmers. So what do? We use our brains and we make a best guess. We think, this place is probably safe. This will never be null, I'm pretty sure. And then we get null exceptions because we're very bad at figuring out whether something will really be null or not. So you may be watching this and thinking, well, okay, you sort of set that up, you use JavaScript. JavaScript is a dynamic language. Can we use type systems to save us? And the answer is not really. The problem is that most languages that have this concept of null allow null to be a member of every type. So you say this function takes a string argument, but technically the compiler says, yeah, it's string, but it could also be null at any point, any time. And so it doesn't really help us. It gets worse, because null as a concept is viral. Uncertainty begets uncertainty, and anytime you have to have checks around whether or not something is present, that uncertainty often tends to spread to any other functions and structures around it. And then finally, as programmers, we tend to abuse the concept of null to represent all sorts of things. So we might use it to represent that there is no value, or that something happened as an error, or maybe even as some programmer-defined special meaning. This is not JavaScript conference. This is Elm Europe, and so let's take it the approach that Elm takes. Instead of the sort of trust no one by default, Elm flips this on its head and says, why don't we just trust everyone by default? Unless you've explicitly told me that this value is optional, I'm going to assume, and in fact I'm going to enforce, that this value must be present. So if we look at the uncertainty problems that we had before, the problem that any value can be missing at any time, well, we fix that just by using Elm. We get that for free by using the language. But there are more issues. And this idea that uncertainty tends to spread is also present in Elm. Elm's maybe type is just as viral as null is in JavaScript and other languages. Also, as programmers, we abuse maybe just as much as we abused null and other languages. So going back to that example that we had in JavaScript, if we kept the same sort of semantics that we had before, any value could be null at any time, and translated that into Elm types, it might look like this. So it's a function to format the name. It takes a maybe user, and it returns a maybe string. And checking if something starts with a vowel, we check maybe string to maybe Boolean. Everything is a maybe. But the difference is, because of Elm's type system, it is going to force you to make those checks. They were there in the JavaScript. We were implicitly making or not making them. So it's not new logic. But here the compiler is going to keep us honest, and it's going to force us to write manual checks. So the actual implemented function might look something like this. Anybody here write a function like this before? Yes. And if you have done that, you probably feel the same way I feel after that. And that is like this. Because that is not sustainable, and there's no way I'm going to have to write this many conditionals to do something as simple as conditionally prepending a star and lowercasing a name. So how might we eliminate the maybe? A strategy that might sort of come to mind, or that's maybe the simplest, is to say, let's unwrap it early. Let's say the moment we get a value that is optional, let's do a case statement, either get the value that we want, or because we have to return something in the case of nothing, let's give it some sort of default value. So default values are a bit of a mixed bag. They're generally good when you're ready to output the result of a function to your view. So if you're about to put it in your HTML, or if you're about to send it over the wire, these are good places to use defaults. But there's one sort of pitfall that I've often seen, and that's where we kind of use the default as a sort of pseudo nothing. So let's take a look at this function here. We're trying to view the name, and we have a function that says getName or default that we saw earlier that returns either the prefix name or the empty string in case it was a maybe. And then in here we have to do yet another case on the empty string to check that it's anonymous or we show the actual name. Now, is this any better? Did we gain anything by doing the default earlier and defaulting to empty string? Not really. This logic is just the same as if we'd skipped the defaulting step and just put nothing in right there. So as programmers, we often like to sort of force multiple shapes of data into a single shape, and then pass it down one distinct pipeline of functions. I mentioned in the beginning, we don't like having to do special conditions. We like to just say, do this function, do this function, do this function, and if we can force it into one shape, maybe we can sort of skip some of them. So passing a default value like empty string is kind of trying to be clever and trying to force that a single path through our logic, and it's kind of a clever way to no-op. So we want to go, instead of stopping and doing that first check and saying, well, if they're not present, skip and immediately do anonymous, we're trying to go through the full chain with this sort of dummy value that's the empty string. So if we do want to say split it and say, OK, sometimes we do anonymous and sometimes we do all this other stuff, this brings up a really important guideline, which is that when dealing with uncertainty, we want to separate code that checks for presence from code that calculates values. So if we look back again at our control flow diagram, we've got all of this logic here. And here's how we would like to split things up. Here's our core business logic. That should be on its own. That should not have any uncertainty in it. And then separately, we have logic that deals with the maybe. So here's what a confident business function might look like. We format the name. Note that in the type signature, there are no maybes. We write the function that we would like to have, no maybes, and we just do our logic the way we do. Of course, in the real world, you will have to integrate with uncertainty that comes from all sorts of sources. And so we also have to handle the maybe. Here we can use the map function to say, format the name of this optional user, but skip that if the user is nothing. And we could do a bunch of operations here if we wanted, every time saying, well, but just skip it if it's nothing. And then finally, at the end, we'd say, OK, now that we've done all the processing, we'll default to anonymous. Another way of sort of saying this guideline that we looked at a few slides ago is that business functions cannot take maybe as an argument. That's just generally a good thing to do with your functions. It keeps the uncertainty on the edges of your system, and the inside is all confident. So that's all well and good, but what about two maybes? Right? We've got users who may or may not be present, but what about also the donation amounts? Those are also uncertain. Can we still apply this in this situation? Well, let's take the same process. We start with a business function that has no maybes, and we say this user with donation, and we format a bunch of things. And note, again, there are no maybes in this type signature. And then, because we're dealing with two maybes, we use the maybe map to function, which allows us to skip over two values and say, if both of them are present, run this function. Otherwise, immediately skip to the next step, which in this case is defaulting to anonymous. Another way to describe this idea is to say, write confident business logic functions and only deal with maybe at the edges of your system, and probably using the appropriate map function. So these are different ways that we can deal with uncertainty that comes from outside of our program. But uncertainty can also come from within. And this is much harder to avoid. For example, we're trying to look up a donor by name. Say we want to filter down the list. And so we're filtering it, but we want just the first result. And list head is going to return a maybe. There's no good way around it. And so our find by name function here, the arguments are string, list user as inputs, and then it returns as output maybe user. Does that violate our guideline from before? Let's add a little bit more clarity. So it's probably best in most cases to not have any maybe at all in your type signatures. But there are some cases where you must have it. And if so, you can have it as the return value, but not as an argument. Now, because it's in the return value, the next time we want to chain something onto this, we are going to have to deal with a maybe again. And so what we want to do is to avoid that maybe that's the output of our function from spreading. We're going to try to quarantine it. And so anytime we combine with other functions, we're probably going to need to use the maybe and then. Maybe and then is made exactly for this scenario when you say it's a function whose arguments are always guaranteed present, but the return value is a maybe. pretty much any time you invoke guideline 2, you're going to need to use the and then function when you want to chain. So with all that, does that mean that maybe is bad? So I've been talking a lot about how to avoid it, some of the problems that it brings. And maybe it's actually a wonderful invention. It adds a lot of clarity to our code. It helps us to be confident by default everywhere. The problem is that it's overused and misused, particularly in modeling. The problem or one of the problems in JavaScript is that every value can be optional. You never know which ones are present. And in Elm, if every value in your type signature is maybe, then you've basically got that same problem that we had in the world of JavaScript. So we're not taking advantage of the guarantees that Elm can give us. Our modeling, too, can often bring uncertainty to our code. So let's look at here. We're sort of using two meanings. There's been a bug in, or a misconception about how we've been using maybe in this project all along. So we have a list of users. But if I say get the head and I get nothing back, that means that there were no users in the list. But because nothing also represents an anonymous user, then if I get the head of this list, I also get nothing. So how do I know? Does nothing mean I don't have a user, or does it mean that the user is anonymous? And yes, I realize this should have a just right here for those of you who are annoyed by seeing the error there. So we can model the difference using union types. So explicitly say we have a donor type, and either you're an anonymous donor or you're a named donor with a string. That way, when we see nothing, nothing actually means nothing. There is no user, not some special programmer inferred meaning. Guideline 0 is really kind of a way to skip all of this other stuff where we're dealing with maybe and say, what if we just didn't have maybe at all? What if the way that we modeled our data didn't involve us having to check maybes because we used the power of Elm's data structures to actually model something that's closer to our problem domain? And a common mistake that we make is trying to force a single shape on our data structures. So if we were now building an interface for adding new donors, and we decide to do it as a sort of wizard. So there's a step 1 where you add the donor's name, then you click a button. Step 2, you're going to put in the donation amount. Because both of those might or might not be present because they come from a form and they're user input, those are both maybes. And if we look at that, that might sound at first like a reasonable way to model, but there are some impossible states. Right here we say there is no donor, and that donor that doesn't exist donated $10,000. I know I would like for the universe to give me $10,000, but it's not going to happen for this charity. And so this is an impossible state. We want to prevent that. And we also would like to avoid having to do all the maybe checking that comes with having 2 maybes. And in a real wizard, you'd probably have 20 or 30. We can model this with a union type. So we have our donor wizard. Step 1, we need to get the donor, but because it's from a form, we don't know if it's there. So that one is a maybe. That is legitimate. Step 2, however, you're not supposed to get to step 2 if you don't already have the donor from step 1. So that one, no more maybe. That one is guaranteed to be there. But the user input from the form is now the donation amount. And then finally, once we've completed the wizard, we have both the donor and the donation amount. No maybes, it is complete certainty right here. So to kind of recap our journey, we started off with null and all of the uncertainty that it involved. We looked at Elm's maybe type and how defaulting can be helpful, particularly at the edges of our system, but that it kind of falls short a little bit trying to skip over maybes. Mapping then allowed us to completely separate our business logic from our presence checking. And then finally, union types allowed us to write data structures that more closely model our problem domain while also removing some presence checks that were unnecessary previously. And these are the three guidelines that we saw. Number 0, just try to model your data structures to avoid maybe in the first place. Number 1, separate code that checks for maybe or presence from code that calculates values. And then finally, for the caveat to that is business functions that return maybe are acceptable, but don't allow maybe as arguments to your business functions. So my name is Joël Quenneville. You can find me on GitHub, Slack. I'm pretty active there, and Twitter. And I've actually printed out a bunch of postcards with the meme. And it's got the 3 guidelines on the back. So I won't be taking questions here, but definitely come see me afterwards, get a postcard, ask me questions, talk about maybe or data modeling. I love those things, and I would love to meet you. Thank you.